Hello, my name's Darren Holmes, and today we're going to be using National Instruments MultiSIM to simulate a fairly simple AC RC circuit. But more importantly, I want to show you the operation of a Agilent type function generator and a Tektronix type oscilloscope. So I'm going to go over the functions of these two pieces of equipment, and I want you to feel confident when we're completed this exercise that you can walk into a lab room and actually use these pieces of equipment sitting on the bench in front of you. So to get started, you need to find National Instrument MultiSIM icon on your desktop. If you've not installed this yet, you may wish to reference my how to install MultiSIM video on YouTube. So just go ahead and double left click on the National Instrument MultiSIM icon. Now you'll notice I'm still in evaluation mode on my license and I have 6 days remaining, so I'm just going to click on Launch MultiSIM. And would I like to extend the evaluation? At this point I'm going to say no. And you can see MultiSIM loads up for me. So today I'm going to do a little AC circuit simulation. So to start with, I'm going to go up to Place. And the first thing I want to do is place a title block. So my favorite title block is a small one. It's example1.tb7. So go ahead and click on Open. And I like to put that in my top right-hand corner. So this is the title block, and you can see it's April the 1st, 2020. So I need to fill in some information here. So one's title and one's document number. So if you go ahead and double-click on the title block, it brings up the dialog box for it. So under title, it's got an ampersand S, so I'm just going to type in example AC circuit. Now the other place to put some information was document number. It's not a very big space, so I just type in my name there. And I'm just going to click on OK. So now you can see I have a title and a document number. So Example AC Circuit by Darren Holmes. So right now this box is highlighted. You can see the little blue squares on the corners. So if you click anywhere on your design, it stops highlighting it. So now we need to place some components. So we go up here to Place, and the first item is Component. So under Group, all groups is going to be fairly large to sort through. So they have it in like subcategories. So the first thing I'm going to do is go to Sources and Power Sources and click on Ground. So every simulated circuit needs a ground symbol. So just go ahead and click on OK. And I'm just going to put it down here and drop it. Now my circuit needs a ground, and also the oscilloscope needs to go to ground, so I need a second ground symbol. Rather than running wires all over my page, it just makes life a lot easier. The next group I need to go to is Basic, and I'd like to put in a resistor. So if I click on resistor, you'll notice all the resistors are of a fixed size. So if I've measured a resistor in the physical world and would like to use it, so say I have a 1.03 k ohm resistor, you'll notice it's nowhere in the list. So if you go to Rated Virtual, they also have a resistor that's rated. So if you click on that and say OK, and now drop that in your circuit. And I'm just going to close this box for now. So it labels it automatically R1, and it comes up as a 1K ohm resistor. So if you double click on it, you'll notice it says resistance 1K. You can go in there and type in 0.03. So that's 1.03K. Click on OK. So now the value of my simulated resistor is identical to something I measured in the lab. So now I can do a simulation based on my physical measurements. So another component I need is a capacitor. So I'm going to keep in rated virtual and capacitor rated. And I'm going to click on OK. And I'm going to throw that in my circuit. So I'm going to close this dialog box. Now, if I double click on my capacitor, I can change the value of it. So it comes up as 1 microfarad. And in the lab, my 10 nanofarad capacitor came in at 13.4 nanofarads. So I'm going to click on OK. So now I have a 13.4 nanofarad capacitor. So using virtual components, I can actually simulate any component I've measured in my lab room. So I'd like to rotate this component, so just do a left click on it and then a right click, and you can do a rotate 90 degrees clockwise or counterclockwise. You can also use Control R or Control Shift R to rotate these. So there's my capacitor rotated. So now to connect some components together, it's up to you how you space them on the screen, but you don't want them getting too cluttered, too close together. So try and leave some space between them. So all I'm doing is doing a left click on the ground, then hold down the left mouse button, and you can drag it all the way around your screen and place it anywhere you would like. So I have to connect to this capacitor. So it's best to leave 2 spaces between components, at least 2 spaces. So now to connect these components, if you go to R1, you'll notice the pointer turns into a crosshair. So if you just left click the mouse button on the crosshair, and now when you move the cursor, you'll notice a wire follows it. So if you move over and then down, it comes down to the capacitor. And it's hard to see, but it puts a little red dot there. So if you do a left mouse click, it connects the wire for you. So it's a red piece of wire. So now I'm going to connect the capacitor to my ground. So this is my circuit. It's a fairly simple circuit. So now I need to put some equipment in there. So down the right-hand side of your screen is your equipment toolbar. So you'll notice right here I have a Tektronix oscilloscope, an Agilent oscilloscope, multimeter, and an Agilent function generator. So just go ahead and click on that, and it brings up the schematic symbol for it. So this is what's going to give power to our circuit. So I'm just going to drop it on my circuit there. So this is what it looks like, and it has 2 connecting wires to it. So if you double left click on the schematic symbol, it brings up this function generator. So you can go ahead and drag it anywhere on your screen that you like. So I'm just going to drag it over onto this side of my screen. So you can see it has 2 BNC connectors on it. One's called sync and the other one's called output. So sync is usually a TTL level output, so that's usually 0 to 5 volts, where output is can be a sine wave with negative and positive peaks. So the output's the one you want to use. So that's the bottom connector here. So you can see my function generator is active right now. It's highlighted. And when I go over to these pins, nothing happens. So click somewhere on the screen and it's no longer active. So now when you come over to the pin, you'll notice you get those crosshairs. You can do a left click and drag the line over to your resistor to make the connection. So that's my function generator hooked up to my RC circuit. The next thing I want to do is bring up the oscilloscope. And in our lab rooms, we're most familiar with the Tektronix oscilloscope. I have a whole series of labs using them. So go ahead and click on that. So this is the oscilloscope schematic symbol. So go ahead and drag that onto your page and do a click to anchor it there. So you'll notice on my oscilloscope I have several connectors on here. The second one over is labeled G for ground. So it needs a ground reference. So I'm going to grab my ground symbol, drag it up close to my oscilloscope, and just drop it there. So now I need to hook that ground up. So when I get the crosshairs, just drag the wire down. Okay. You can see there's a little red wire there, so make sure whenever you put any components and wire them up that you do get that little red wire, or else you never really know if they're connected or not. So channel 1, I want to look at my function generator, so I'm going to bring it down and over, and then bring it down to, oh, look, it went through the R1 description. I don't want it to do that. So I'm going to move my cursor up, and then I want to anchor it at that point. So I use the left mouse button, and then when I move the cursor down, you'll notice the wire stayed there. So when it makes contact with the other red wire that's connecting the function generator to R1, there will be a little red dot there. So I'm going to go ahead and click the left mouse button, and that little dot indicates that there's a connection there. So then I'm going to connect channel 2 to my capacitor where it meets the resistor. So channel 1 is looking at the voltage across the resistor and the capacitor, or you can say it's looking at the output of the function generator. Channel 2 is looking at the voltage between R1 and C1 with respect to ground. So channel 2 is actually looking at the voltage drop across the capacitor. So now I'd like to see what my oscilloscope looks like. So I'm going to double click on it, and you can see it looks like a real oscilloscope. So I'm going to go ahead and move that to the bottom left hand corner of my screen. So once you're happy with your circuit, it's always a good idea to save your work. So to save it, I'm going to go to File. I'm going to go down here to Save As. And you can see it saves it into a directory. And it's a design1.ms14. So where it says design1, I'm just going to put in a file name of my choosing. So once you've selected a file name, you can click on Save. Now just before I do that, I want you to notice on the top of the screen, we have design1-multisim-design1 with a little asterisk. Now watch what happens to that when I hit the Save button. Up here on the top of my screen, it says Example AC Circuit. So now it's actually saved it. Now if you make a change to your schematic, so I'm just going to move a component here. So all I did was move the component. You notice a little asterisk shows up here telling you that you have not saved this change. So now you can go to File and click on Save. Before we start the simulation, I just want to go over a few sine wave facts with you. First thing to remember is a complete circle covers 360 degrees. When we open up that circle, we end up with a sine wave. You'll note that the length of the sine wave covers 360 degrees. We call the length of the sine wave the period, and it's measured in time. In our case, it's usually measured in seconds, or milliseconds, or microseconds. The period is relatable to the frequency. The frequency is equal to 1 divided by the period, or the period is equal to 1 divided by the frequency. So on our horizontal scale, on our oscilloscope, we're going to see time. So on the vertical scale of our oscilloscope, we see amplitude, and amplitude is usually measured in voltage. So when you look at our sine wave example here, we start with a zero crossing point. So at 0, 0, we start our waveform, and it goes in the positive direction until it reaches its maximum or peak voltage. So this is going to be plus 1 volt in our case. It's also 90 degrees from the start. So then our waveform continues downward until it reaches 0 volts. So this is our zero crossing point. And at this point it's 180 degrees. Because it's going downward, we call it our negative zero crossing. It continues downward until it gets to its maximum negative peak. In this case, it's minus 1 volts. It then continues upward until it goes through the next zero crossing. We refer to this as the positive going zero crossing, and that's at 360 degrees. Now sine waves repeat themselves, so from this point it comes back to the start and starts over again and just continues on. So this point here, where we have the 0, 0 crossing, we usually set that up as a trigger point so that the sine wave stays stationary on our oscilloscope. One last point I want to bring to your attention is it has a maximum positive peak of plus 1 volts and a maximum negative peak of minus 1. So if we start at minus 1, we have to go up 1 volt to get to our 0 line, and then up 1 to get to our maximum peak. So in this case, we say our sine wave is 2 volts peak to peak. So now we can start our simulation and see what this will look like on an oscilloscope. So before we start our simulation, we need to activate our power source. So just like in a real lab setting, you should set up your equipment before you power up a circuit. So when you take a look at our function generator, you'll notice the BNC connector. The second one down has this little whitish symbol with crosshairs on it, indicating that that is hooked up. When we take a look at the oscilloscope, you'll notice the ground has a little white crosshair on it, as does channel 1 and channel 2. So this indicates to us that these connections are correct. So the first thing we want to do is turn on our function generator. So press the power button, and you'll notice it starts at 280 millivolts peak to peak. So I'm going to increase that. So all I'm doing is using the left mouse button and holding it down and slowly rotating the dial. So when you get it 2 volts peak to peak, we have 2 volts peak to peak set up here. Now the next thing we need to adjust is the frequency, so click on the frequency button down here. If you want to go back to amplitude, click on the amplitude button. So looking at the frequency, you can see we're starting at 1 kilohertz. This little symbol beside the kilohertz indicates a sine wave. So across the top here we have different functions. Next one over is a square wave, and that's its symbol. Next to it is the triangle wave, and that's its symbol. So today we're going to use a sine wave. So make sure the sine wave symbol is displayed. Next thing we need to do is turn on the oscilloscope. So just like a real oscilloscope, we have to turn on our simulated oscilloscope. So now that we have our equipment activated, we can now start our simulation. So you'll notice on the toolbar there's a little green side triangle, and it says Run. You can also go up to the menu bar and click on Simulate, and it has a Run. Or you can press F5 to start your simulation. So we've started our simulation, and the first time I ran a simulation I had nothing on my oscilloscope. So if you end up with nothing on your oscilloscope, make sure you have set up your function generator correctly. Stop your simulation. You'll notice there's a square red symbol on the menu bar. Just click on that and it stops the simulation. And then you can click on the green button to start your simulation. Now your waveforms may not look like this when you start yours. Just like real oscilloscopes, there's an auto set button. If you click on the auto set button, it tries to find the best settings for your waveforms. So you can see in this case, we're seeing a lot of cycles of the sine wave. The vertical settings, now this is a 4-channel oscilloscope. We're only going to be using 2 channels because that's the type of equipment we have in our lab rooms. The vertical settings are for volts, and you'll notice they're labeled volts per division. So in our case, you can see channel 1 is set to 2 volts per division. So the yellow trace here is channel 1. So you can see it goes up half a division. So all these little squares we refer to as divisions. So it goes up half a division. So half a division is 1 volt. We have channel 1 and channel 2 menu buttons. If I click on the channel 2 menu button, it brings up channel 2 settings. If I click on channel 2 menu button a second time, it turns off channel 2. So now we're just looking at channel 1. If I press the channel 1 menu button, it brings up the settings for channel 1. Right now the coupling is on DC. So you'll notice the 1 on the display on the side of your oscilloscope, that's the 0 line. So you can see we go up half a division and then down half a division. Each division worth 2 volts. So we go up 1 volt, down 1 volt. We can position our waveform with the position knob. One way to do it is hold down the left mouse button and rotate the knob. So we want to get it as close to 0 as possible. So you'll notice at the bottom of the screen, it's telling us where that knob is rotated to. We can also click on either side of the little white line on our position knob, and it will move it in increments. So practice moving the knob until you get to 0 volts. So we want the 1, which represents the 0 volts line, to be on that horizontal axes that go across the center of our oscilloscope screen. This is an AC circuit. We have no DC on it, so if you click on the coupling, you can make it an AC waveform. That just eliminates all the DC voltage on it if there was any. Now I'd like my waveform to be bigger so it covers more of the screen. So for that, we have the volts per division knob. So if you click on the right side, it makes the waveform smaller. If you click on the left side, it makes it bigger. So at 200 millivolts per division, it goes off the screen. That's not desirable. So at 500 millivolts, it seems to stay on the screen. Now there seems to be a lot of it all bunched up, so we would like to open it up. So to do that, we have to adjust the time setting. So if you click to the right, you can see it bunches it up more. If you click to the left, it seems to open up your waveform. So at the bottom of the screen here, we can see the time is set to 200 microseconds. So our waveform seems to cover one division, which is 200 microseconds, two divisions, 400, 3, 6, 4, 8, 5 would be 1,000 microseconds or 1 millisecond. So if you take 1 over 1 millisecond, you should end up with 1 kilohertz. So you'll notice my waveform does not go through the vertical and horizontal zero crossing line. There's two ways to adjust this. We have the horizontal positioning knob, and we also have the triggering knob. So triggering is finding out where the zero crossing is. So if I click on Trigger Menu, you'll notice it says Source Channel 2. We need Source to be Channel 1. So here we are, Source is Channel 1. So where is it triggering? Where this white arrow and this yellow arrow meet. So I can adjust my trigger level, and as I do that, it will actually move my waveform. Keep in mind, if you lose your simulated signal, turn off your simulation, and then restart your simulation. So now you can see that my simulation is actually going through the zero crossing line here, both horizontally and vertically. So at this point, I want to check channel 2. So channel 2 is not active. So if I press on the channel 2 menu button, you can see the channel 2 waveform. Now channel 2 is set at 2 volts per division. So I'm going to adjust my volts per division until it is on 500 millivolts. So channel 1 and channel 2 are both on 500 millivolts. I want both of them to start on my 0 horizontal line. So channel 2, positioning knob, I'm going to rotate it until it's at the horizontal zero crossing. So you can see at 1 kilohertz, both waveforms are fairly close to each other, but there is a small phase difference. So I'm now going to change my frequency. So I'm going to increase my frequency. And you'll notice as I increase my frequency, I get more and more cycles being displayed on my screen. So I'm going to stop at 10 kilohertz. Now when things get bunched up on your screen, we adjust that by changing our seconds per division. So you can see I have a larger phase difference when I'm at 10 kilohertz than when I was at 1 kilohertz. It would be nice to be able to measure this phase difference. In fact, it would be nice to know what our input voltage is and what our voltage drop across the capacitor is. We have a few features on this oscilloscope that allow us to do that. The first one is the measure button. So if you click on the measure button, it brings up the measure menu down the side of your oscilloscope screen. So you'll notice right now everything says none. So if I click on the first button, it says source channel 1, type none. So if I click on the button beside type, I can change it to channel 1 frequency. I can then press the back menu item. So channel 1 says it's a frequency of 10 kilohertz. The next button down, I'm going to click on it. It's channel 1 and type. I'm going to change that. I can get the period. So you can see channel 1's period is 100 microseconds. I'm going to press back again. On the next menu item, I'm going to click on its button, source channel 1, and in this case, I don't want type frequency or period. I don't want the mean voltage, I want the peak-to-peak voltage. And remember, we set up our function generator to output 2 volts peak-to-peak. So our oscilloscope's saying channel 1 is at 2 volts peak-to-peak. So I'm going to click on back. Now on the next button, I want to look at channel 2. So where it says source, I'm going to select channel 2. Where it says type, I'm going to select peak to peak. So channel 2's peak to peak is 1.51 volts. So I'm going to click on back. So rather than trying to measure how many divisions and how many of these little gradicules my waveform covers, I can put on the measurements and it will tell me what the voltage peak to peak of channel 2 is, and it's 1.51 volts. However, if I want to measure the phase difference, I need to know what the difference is between the two waveforms. So in order to do this, I have another feature on my oscilloscope called cursors. So if I click on cursors, you can see right now they're type off. So if I click on the type button, I can select voltage cursors. So this allows me to measure peak-to-peak voltage. I don't want voltage cursors, I want time cursors. My source is channel 1, so it's going to measure the time difference between channel 1 and whatever I select. So right now, cursor 1 is at minus 100 microseconds. So that indicates that cursor 1 is somewhere over on the left-hand side of the screen. Using my channel 1 position knob, if I rotate it, I can change where cursor 1 goes. So typically, we move cursor 1 over to the 0 crossing line for channel 1. So this is the positive going transition at the 0 crossing point. Cursor 2, and you'll notice right underneath the position knob it says cursor 2. If I rotate that knob, my second cursor comes off the right-hand side of the screen, and I want it to go through the second waveform at its zero crossing. So you can see the time difference between the two waveforms using the cursors is displayed as the delta. In this case, the delta is 10.6 microseconds. So if you take 10.6 microseconds and divide it by the period of the waveform, multiply that by 360 degrees, you'll come up with a phase angle. So that calculation works out to 38 degrees. So when you take a look at your waveform, we know the peak happens at 90 degrees, so halfway between the zero crossing and the peak should be about 45 degrees, so this happens a little bit before the halfway point, so 38 degrees looks like it's about correct. So I'm going to go back to the measurement screen, and that will turn off the cursors. There's one last thing I would like to show you. We'd like to know what the voltage drop is across R1. Now, unfortunately, we can't measure directly across R1 because the outside of the BNC is ground. So if I try and put a scope lead across R1, I will actually short out my capacitor. So we have two ways to measure the voltage drop across R1. One is to swap R1 with C1. Changing their positions will not affect the circuit because it's a series circuit and the same current flows through both components. Rather than changing our circuit, we can also find out what the voltage drop across R1 is by taking the total voltage across the circuit and subtracting the voltage across C1. So to do that on our oscilloscope, we have something called a math menu. Now, when using the math functions, it's important to have both channel 1 and channel 2 on the same volts per division. It's also important the waveforms are shown on the oscilloscope screen, because if the waveforms go off the oscilloscope screen, the measurements are no longer going to be valid. So I'm going to click on the Math menu button. The operation is set up for plus, so we want to subtract channel 2 from channel 1. So click on the operation, and we now have minus. The operation we want to perform is channel 1 minus channel 2. So make sure that is selected. And now when we look at our oscilloscope screen, you can see channel 1 is our input voltage. Channel 2 is the voltage drop across our capacitor. When we look at this, we say it is lagging. Remember, in a series RC circuit, the current leads, so the voltage drop on the capacitor must lag by 90 degrees. When we look at the voltage drop on the resistor, you can see it is leading. Once again, if we want to find out what it's leading by in degrees, we can go back to cursors. And in this case, we can change our second cursor so that it goes through the zero crossing of the red trace, which is our math function, or the voltage drop across our resistor. So in this case, it's 15.2 microseconds. The phase for R is equal to 15.2 microseconds divided by 100 microseconds times 360 degrees, which works out to 54.72 degrees. So when you add these two phase angles together, we end up with a total of 92.82 degrees. So ideally it should have been 90 degrees, so we do have a little bit of error when we're trying to estimate exactly where those zero crossing points are. Now I know you're wondering, how did I get that to display on my screen? I went up to Place and I went to Text. So it gives you a little eye symbol as your new cursor. So just click where you want to place the text and then just type in what you want to say. And when you're done, just click on the little X in the text box and click elsewhere on your screen. You'll notice the text is highlighted so you can actually move it around. So you notice it's still active, so click somewhere else on your screen. Now before you make any modifications to your circuit, it's important to turn off your simulation. Notice when you turn off your simulation, you lose part of your screen display. So turn on your simulation, and you'll notice there's a pause button. If you click on the pause button, you may also lose part of your display. Sometimes you can time it correctly so you can maintain your entire display. And now when you stop your simulation, everything will be displayed on your screen. Now there's one last item I'd like to show you. You'll notice in Windows 10 you have a search bar. If you click on that, type in snipping, you'll notice we have snipping tools and snip and sketch tools. If you just click on the snipping tool and click on New, notice your screen goes slightly dim and you get a crosshair show up. So in that crosshair you can go to a point in your screen and just drag a box around your circuit and your instrument. And that captures part of your screen. So you now can go ahead and you can actually save this. So you can go to File, Save As, and you can save it as a PNG file, which is higher resolution, or you can save it as a GIF or a JPEG. And this will allow you to put this particular simulation into a Word document for presentation to your professor. So I think this concludes the introduction to simulation using an oscilloscope and a simple AC circuit. So please don't forget to subscribe, and I'll be posting more videos shortly.